Atau sampun sensei.
Hai.
Okay, it's 10 o'clock in the morning. Assalamualaikum warahmatullahi ta'ala wabarakatuh. And ohayo gozaimasu to all of the audience. I would like to welcome our distinguished guest today, Professor Dr. Suzumori from Tokyo Institute of Technology. And today we're going to have a special talk to get together entitled the Soft Robotics Pioneering E-kagen Sciences. And Professor Suzumori will be sharing some of his experience throughout the journey in developing the soft robotics area. So a little bit about the session today. So this session is organized by the Department of Deputy Vice Chancellor of Research and Innovation, and in collaboration with UTMShine, one of the body under the TFT and CTI office, as well as Cairo. So Cairo is the Center for AI and Robotics from UTM. So I'm Ahmad Atif Muhammad Fauzi, the moderator for the session, currently the director for Cairo. And I would like to invite everybody to be together with us today. And I'm welcoming everybody to join this session. A little bit about the speaker. Suzumori received his PhD from Yokohama National University in 1990. Professor Suzumori had worked for Toshiba Research and Development Center, R&D Center from 1984 to 2001. for Micro Machine Center from 1999 to 2001, and for Okayama University from 2001 to 2014. And currently, he has been a professor in Tokyo Institute of Technology since 2014, and the program manager of Soft Robotics Project in Japan, which started in 2018. Main work other than soft robotic is in the flexible micro actuator, micro robots, electrostatic actuator, artificial muscles, Giacometti robot, biomimetic robotic, IPMC, and others. And he has been a very good speaker in many international events. And we're grateful today to be together with Professor Suzumori with his busy schedule. And like also a little brief about the session. This topic will be regarding soft robotic pioneering E-kagen Sciences. The project is under MEXT Project that will be introduced by Professor Mori that was started in 2018 with a big budget of 1.2 billion yen, and it will be conducted within 5 years. So Professor Suzumori will discuss about the significance of soft robotics and as one of the value changer. And Professor Suzumori will also discuss about the word of E-kagen. So some of the Japanese friend maybe understand E-kagen word, so they have two meaning maybe. So maybe Professor Suzumori can explain how it relates with soft robotics. So without further ado, I would like to invite Professor Suzumori. So we have a session around 30 minutes, and we're going to have also another 20 minutes for question and answer, and roughly around 11 a.m. in Malaysia time, we're going to finish the session. So I would like to welcome Professor Suzumori. Hi, Sensei Dozo.
Thank you very much for your introduction, Atif. And I will share my. これ画面が見える？
はいはい、OK。見えます。
Okay.
Hi.
Hello everyone. Thank you for inviting this lecture meeting. And I'm Koichi Suzumori from Tokyo Tech. The title of my talk is Soft Robotics Pioneering E-kagen Science. And E-kagen is one of the keywords in our project. And I will explain about it today. And as you know, soft robotics is a new discipline which has become very active in these 10 years in the world. These are examples. These are examples of symbolic images of soft robots which we are aiming at. And some of you might think this picture is not honest in academia. But I believe accepting this kind of irresponsibility to science is an essential idea of software robotics. And I have developed various types of software robots as shown here for over 30 years. And I have 4 topics today. One, what's software robotics? Then MEXT Project on Soft Robotics. MEXT stands for Ministry of Education Japan, and several examples of soft robots in my laboratory, and soft robotics pioneering E-kagen science. Let me start with what's soft robots. This slide shows the background of soft robotics. We can say that the can say that conventional robotics is based on the value of conventional engineering, that is the speed, force, accuracy, and certainty. This results in a great success in industries, as you know. But I'm afraid that we are facing now the limit of conventional robotics. Current robotics still cannot realize some performances in our daily life, which living creature easily uh, do it. For example, it is not easy for today's robot to hang a baby with a moderate touch. Soft robotics can be said a new robotics based on the value of biological systems such as flexibility, adaptability, and E-kagen. E-kagen is a keyword, and I will explain later. On the other hand, many new researches on softness have been born recently in various fields such as mechatronics, material science, and computer science. Example are soft electronics and soft machines in mechatronics, and gel 3D printing, and biological materials in material science, and soft computing and biocomputing in computer science. And an interesting point is that these technologies are bad technology from the viewpoint of conventional robotics. Robot arm, which is easily deformed by the external load, is a bad mechanical design in conventional robotics. These materials are fragile and unstable, which means a bad material in conventional engineering. Recently, AI returns a different answer each time. They can be said bad technology from the viewpoint of conventional engineering, while they actually work well. Applying these software technologies to conventional robotics will create a new academia discipline, software robotics. That is the basic idea of software robot. Let me explain in more detail. Conventional robot, sorry. Conventional robot consists of rigid metal body, precise servo motors, and careful programming. This results in speed, force, and accuracy, and reliability, as you can see at this. Does this movie, can you see this movie?
Yeah, okay.
Okay, moving?
Yeah, moving.
Okay. The conventional robots work very well in the environment, such as in factory production lines, which are designed strictly by engineers. But the conventional robots, sorry, I'm afraid this movie doesn't work. I don't know, but conventional robots are still very difficult to work in our daily life. There are many uncertainties and unknown problems exist. This is an example of a robot tipping over because it could not grab the handle. I'm not bringing a special case of failure. This is what often happens when we bring current robots into our daily world. We can say the controller algorithm is too precisely too precisely designed for robot to respond to unexpected events. So if unexpected event happens, which programmers didn't expect, the robot will get terrible problem. In contrast to these robots, living creatures consist of a soft body, flexible motion, and adaptable intelligence. This results in flexibility, adaptability, and e-kagen. For example, they show the shape adaptability and the passive force control as shown here, and also they can perform dynamic motion using their flexible body. I will show several examples of software robots. This is my first software actuator named Flexible Micro Actuator, FMA in short. It's made of fiber reinforced rubber and driven pneumatically. It shows very good shape adaptability to the object and distributed force control. This is a pipe inspection robot. It consists of two-wheel drive mechanism and the soft actuator for steering, FMS here. This is a 2-inch pipe. The point is, even if the robot is stuck, repeating the driving the FMA deformation randomly makes the robot release. At this time, robot is stuck in this point. But driving the FMA randomly makes the robot release. This is an example of a 20-meter long arm. It has a small camera at the tip. This is the image from the camera, and this arm enters this window roof to approach the pipe to inspect it. The arm can contact the construction with no damage because it is very soft. What's interesting in this example is that the arm can find the approach path to the pipe by itself after repeating contact with the surroundings. Instruction from the operator is very simple. Just go ahead. This is a very different from conventional robotics approach. Conventional robotics would use a very stiff and heavy arm and laser rangefinder for recognize the environment, and the computer finds the approach path in a very logical manner. But software robotics work in a very loose manner. This is a self-propelling colonoscope. It is driven pneumatically. This shows the inserting test using this model. This is a view from the scope camera. It moves well in the model. This is a jumping robot. The soft robot can use a big energy in a short time, which is stored in their body as elastic energy and is released instantaneously. This is a big advantage of soft robot. This is an inchworm robot. It consists of two motors and elastic body between them, which is a rubber band, which are bent by wires driven by each motor. These two motors are not servo motors, but open control motors. This means the motion of the motor depends on the load. When the load is big, motor speed decreases, while when load is small, the motor speed increases. This causes several different motion patterns of the rubber band. depending on the surrounding condition. This means a soft robot gets an adaptable motion pattern by itself. This kind of adaptability realized mechanically is often found in software robots, and I believe that is one of the big advantages of software robots. And this is a rubber body mimicking an octopus leg. Some computer scientists are looking at software robots as a computing tool. Professor Nakajima is looking at this rubber as a computer. As you know, dynamics of this kind of continuum body is expressed by the partial difference equation. This means a rubber body includes a lot of information in its inside. Compare with the conventional robot, which has a limited number of information corresponding to the number of joints. So Professor Nakajima says that a soft robot is information rich. And by using this rich information, it has a great potential to work as a computer. He is working to use software robots as a computer. Okay, let's move to the next topic. MEXT Project on software robots. MEXT stands for the Ministry of Education Japan, and Kakenhi is one of the most popular research funds for academia in Japan. And there are several types of projects in MEXT Kakenhi, and software robotics is a team project where about 30 research groups are working. The official project name is Science of Soft Robot, Interdisciplinary Integration of Mechatronics, Material Science, and Biocomputing. As shown in this name, an important point of this project is interdisciplinary research. Many researchers from various fields are working in this project. The head investigator is me, and the project is a five-year project starting 2018. The budget is about 1.2 billion Japanese yen. And many researchers are working in this project, gathering from various fields such as mechatronics, of course, material science, computer science, and biology and zoology. It's a very interdisciplinary project and interesting. This form is, for example, a photo of a giraffe dissection. I briefly introduce some activities of this project. We have three groups. A01 group, flexible body. In conventional robotics, the body doesn't change, but the body of software robots is easily deformed and easily changes mechanical properties as time goes on because they sometimes use unstable materials. This problem can be solved with conventional robotics. We have three research groups: elastic tank, growing, and restoring body, and soft wing. Each is a very interdisciplinary project. For example, in this project, experts in robotics, mathematics, and zoology are working together on elastic trunk. In this project, experts of biomimetic robots, fluid analysis, and birds are working on flexible wing. And the A0 groups passes the flexible motion. We have three research subjects of energy harvesting skin, soft artificial muscle, and gel robot mechanism to realize flexible motion. This is my group working on artificial muscle. In this group, two experts in mechatronics and two in polymer materials. Two experts in polymer materials are working together. Chemists develop new materials and we make them to artificial muscle. And A03 group passes a flexible intelligence. This group creates a new mathematical model and information processing for handling continua. This subject is working on thinking elastomer, where information processing is scientists and material science are working. This is intelligent gel. In this gel, self-oscillating chemical reaction occurs and gel is working independently. And this is an interesting example of machine learning based on polymer property. This soft robot sings a famous Japanese old song, Kagome Kagome. Can you hear?
Yeah. We can hear. Okay.
Okay. And these are examples of result of a project. The project continued another 2.5 years. So I'm sorry, we don't have enough time today. So I will just show these thoughts and skip explanation. Okay. This is our future vision of soft robots. This is the end of this project, and our project focuses mainly on academic development, but we want to extend the result to real society, working with industries and other projects. And we want to extend these results to science of soft artifact and E-kagen artifact. Okay, next, I will show several other examples of soft robot in my lab. These are all pneumatic rubber actuators. They consist of rubber body, which have internal chambers. Applying air pressure into the chamber, the rubber deforms and they work as an actuator. There are many actuator robots. This is a miniature hand. Each finger is 2 millimeter in diameter. And this is a contact lens. And the control algorithm is very simple. No sensor and no feedback in this case. The air pressure is controlled by on-off valves. We don't use analog valve here. As each finger has 3 internal chambers, so the hand has 9 chambers in total. So this hand is controlled by 9-bit sequential on-off code. Soft robots can work with very rough instructions without detailed programming. These are walking robots, and this is a self-propelling colonoscope, and these are working as a conveyor. And this is a FMA array. This is a FMA array, which is fabricated through stereolithography. The base of a plate in which air supply thin channels are fabricated also through stereolithography, and on that base, 16 FMAs are fabricated at the same time. This is a manta swimming robot. And this is interesting, this shows the structural color changing with the rubber deformation due to the change of the pitch of the grating fabricated on the rubber surface. Okay, I'll move to the next topic. Do you know magnet muscle? It's a pneumatic rubber muscle, originally invented in Germany in 1948. It's very old and well-known artificial muscle. It consists of rubber tube and braided cord around it. Applying the pneumatic pressure into the tube makes the muscle contract in the actual direction. 4 years ago, I have established a startup venture company, S-Muscle, named S-Muscle, which has commercialized thin magnet muscle, which is 2 mm to 5 mm in diameter. We are weaving the muscle to realize various active fabrics. These two examples are contracting fabrics. What's interesting is that they show bigger contracting ratio than that of original single muscle. These two fabrics show bending motion. They are applied to power software. Please watch the TV program where two reporters are talking about the feeling of use. You can see here what she talking. This is another reporter on another TV program, so you can know the another feeling of use, another opinion of feeling use. This is an application to musculoskeletal robots. We imitate the bone and muscle structures of a human body based on human anatomy. What's interesting in this project is that similar structure results in similar properties. This robot shows several kinematic and dynamic properties similar to the human body. This robot has a very redundant mechanism. For example, one leg has 6 degrees of freedom of motion, but 50 independent muscles are working to drive it. A very redundant system. It would be difficult for conventional motors to drive this kind of redundant mechanism because conventional motors are too stiff to work in cooperation. But this muscle can do it because of their softness. Next, I will talk about a powerful soft robotics and acting. I'm very happy to talk about this topic because recently I'm focusing on this topic. I'd like to propose a new research field in software robotics, which I want to call power software robotics. I'm afraid that some people might think that soft robots generate only small force, but I'm afraid this idea is not correct. There are many examples in nature which show both power and flexibility. I believe that the ideas of softness and power are independent concepts, and I believe we can develop powerful and soft robots. I want to introduce some of my works based on this idea. We are developing a hydraulic McBain muscle. We can apply 5 megapascal hydraulic pressure, which is about 10 times bigger than that of pneumatic. This means hydraulic McBain muscle generates a force 10 times bigger than the pneumatic muscle. We are working with a Bridgestone company to develop strong and durable muscles. For example, this muscle is 16 millimeter in diameter and generates about 1 ton contracting force. We have applied this muscle to several power robots, which is powerful yet still shows a good shape adaptability. I will show two examples. This is a long arm, 7 meter in length, which consists of contracting muscle and extending muscle. Combination of these two types of muscle generate a big moment. This is very similar to the elephant trunk, where some muscles work to support the compressive stress and the other muscle supports the tensile stress to generate big moment. And this is our recent work. We are working with the giraffe anatomies and developing a giraffe robot. Giraffe neck is a typical example in nature which shows flexibility and power. Okay, this is another software actuator we are now developing. Functional polymer. Functional polymer driven by electrical input are generally called EAP, electroactive polymer actuator. There are many types of EAP and IPMC, which I will talk today, is one of the most typical EAP. It is made of functional polymer PEM and thin electrodes fabricated on both sides of PEM. When we apply the voltage to the electrode, cation and water in PEM move in the negative electrode side and the actuator bends. This actuator was originally invented by Dr. Omuro in 1991. These are examples of our robots. We are fabricating them in-house from chemical liquids using several new processes. This shows an example of our very new fabrication process. We fabricated them in-house like this. We have several, this is a cathode fabrication method, and this is a chemical electroplating, and we have other fabrication process from the chemical liquid. This is a process using a paper, and okay, these are robots fabricated in our laboratory. It's just a monocytic seed membrane, but it moves very smoothly by applying the voltage like this. I'm sorry, I don't have enough time, so I will skip it here. And we have two YouTube channels, where you can see many other robots, including this movie. And so please visit us. You can search in YouTube by Suzumori. Okay, let's move to the last topic, software robotics, pioneering E-kagen Sciences. I believe software robotics is a value changer in robotics. Software robotics realize shape adaptability, back-drivability, passive force control, stress dispersion, gentle touch, essential safety. However, these features are bad features from the viewpoint of conventional robotics, which conventional robotics has been seeking for force, speed, and accuracy. For example, robot mechanism which with low stiffness is generally bad in conventional robotics, while soft robotics accept it and use it and realize gentle works easily. I believe essential idea of soft robotics is accepting ambiguity and uncertainty and using them to make robots work in appropriate manner. We have an interesting Japanese word, E-kagen. This word has two opposite meanings. One is a negative meaning, ambiguous, irresponsible, sloppy, unreliable. The other is a positive meaning, moderate, adaptable, appropriate, suitable. I believe this word represents two aspects of robotics, and soft robotics can be said and E-kagen robotics. E-kagen is found not only in robotics but recently found in several other scientific fields. For example, conventional computer science has been seeking power, certainty, and reliability, while recently AI returned different answers each time. This can be said very uncertain. And material science has been seeking for stability and strength, while they are now developing unstable material. In the background of these E-kagen trends, I think there is a historical meaning. In the past, the power and accuracy have been the most important for human beings to survive and grow the society. But these purposes have almost been achieved after the Industrial Revolution and the IT Revolution, and gentleness and flexibility become much more important for sustainable society. I believe we are now at a historical turning point of science and technology, and this caused a value change, and a typical example is economic trend. What's interesting is the idea of economy has been existing in nature and industries since before. For example, soft body weeping will realize toughness by allowing copy error of DNA. Living creatures are evolving. By giving a poor positioning accuracy, the robot arm works well. Wine quality. Wine quality depends on the year of production, but this can be said about quality control from the conventional viewpoint of industry. But winemakers accept this variation and use it to sell vintage wine at a high price. As shown in these examples, I believe E-kagen concept of accepting ambiguity and uncertainty and using them to do in an appropriate manner is a very natural idea and can be accepted in the future science and technology. And I believe that E-kagen can be the basic idea for designing and developing new software, actuator, and robot. And I think that I believe the software robot can be the pioneer of this new trend of E-kagen. Okay, thank you very much for your attention. Thank you.
Okay, thank you very much, Professor Suzumori, for your very interesting talk. And we are now would like to open for the question and answer session. So if you have any question, you can leave the question in the comment area in the Webex, or if you are streaming live from Facebook, you can also put your comment or question there. For those who are in Webex, you can also ask the question directly. You can unmute your microphone and you can ask or give some comments to the session that we just had. Okay, we can open the session now. While waiting, maybe Professor Suzumori, maybe I can start with one question. As you have presented that the soft robotic is having both the advantage as well, or maybe the disadvantage in terms of the low accuracy, as well as the low force of the structure. So, how do you think soft robotics can be used in real application, for example, in commercialization? Do you have any comments on this one?
Okay. It depends. I think the soft robot has a great potential to be applied in various fields, and it depends on the field, applied field. And in my opinion, one big potential application is a field where the physical contact between the human body and the robot are required. And for example, the caring, health caring or medical and nothing, and also human machine interface for between the cyber and physical world. That's where I think where the power and the soft power and the accuracy, which are very important in the commercial robotics and engineering, are not always required. So, that is a one potential application. And but I think that software robot has many potential. It I said that software robot don't pursue the accuracy, but it can realize the accuracy also. It depends on application. Because the software robot and software actuator has no parts or friction parts, sliding parts. It depends on the deformation of the material. So it moves very smoothly. So if we can get the accurate position feedback, we can control the software robot with very high accuracy. But in my opinion, I'm afraid it is not a very good application area, but it depends.
Okay, thank you very much, Professor. We have another one question here by
The
Abdurrahman.
chat box,
Hello? Yeah? Yeah. The question was answered clearly. Okay, we have another one question by Abdurrahman Zayain. What is the type of motor that is used in soft robotics project? Is there any motor used in soft robotic project? or is it only solely by air compressor or by hydraulic tank? Is there any hybrid maybe in terms of having soft robotics plus motor?
Not only in our project, but all over the world, many types of new actuators for soft robots are being developed. You can find many interesting new actuators and motors in YouTube. Very new. Every day, new actuators are submitted in the web. And in, in my case, I have started from pneumatics. But at current, we have, in my laboratory, we have developed the pneumatic, of course, hydraulic, and IPMC, which I talked today, EAP, electroactive polymer. And we have two types of electropolymers. One is the IPMC, ion conductive polymer, and the other is dielectric polymer. Dielectric polymer is a kind of electrostatic actuator, and which are variously being developed in the world now. And also we are working on the SMA shape memory alloy, and there's some piezoelectric, polymer piezoelectric. So various kind of actuators can use they are still competing now. So I don't know which is the best one, but many kind of actuators have the potential to be the key of the software robot in the future.
Okay, thank you very much, Sensei. We have one question from Associate Professor Nafia. I think this is Oka Sensei teammates last time. Professor Hanafa is asking how soft robotics can play a role in COVID-19 detection or prevention, or if you have any projects related to COVID-19 using soft robotics.
Sorry, I don't understand.
Okay. Do you
Can you see the chat box?
yeah. This one is from Facebook. I will paste this.
Okay.
So he was asking about how robotic can play a role in COVID-19 in this current polemic of COVID-19. Is there any projects or maybe idea in using soft robotics?
It's a very important point. And we are now talking about the topics in the project. It's very important. And maybe I'm very sorry, but this situation will continue for not finished in short time. So, well, I have two ideas. One is physical interaction. At current, we are talking this web, but we are just communicating the sound and image. I want to touch your shoulder of Atif now. So such a physical interface, soft robot can be a potential for example, shaking and hanging with no dangerous contact or COVID. And the other is a more practical one, or for human wear. protect the hobby. For example, of course, for example, the mask. Our current mask is, have two big holes through which the COVID easily. If we make the hole small, so it is difficult to breathing. So my idea is which has a big hole, but we apply the electrostatic force here to protect the virus and also kill them by there are many potential techniques to kill them, but my idea is to make such kind of functional mask with using a soft technology.
Okay, we have another few question. The time is still available. This is a question by Nurul Izzati. She is asking for opinion. Do you think that soft robotic will have a future on developing something like emotional assistant animal, like something that can assist people for their emotional health? Do you have, I think, like what you mentioned regarding the hugging, I think maybe you can relate with the emotional assistance.
Emotional assistance.
Yeah.
I have a yes. Can you? I'm sure if I can find the I want to show the very interesting movie. This maybe this one. Okay, can I share the? How can I? I can't find. Okay, okay. Can you hear? No.
Uh,
You see?
yeah,
Can
we can see the video. We can see the video.
video, but no sound,
Yes.
right?
Yeah.
Okay, no problem. This is application to supporting a piano playing. This 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 person has no ability to play the piano, but we use our soft muscle, and which teaches, which guides the fingers to play the piano. But so I think I say this project I named anyone can be a great pianist. And what's important here is the graph. Graph guide us to the on the standard finger motion based on the musical score. And the important point is that the player can add some modification based on his uh, emotional emotion. So we don't need severe hard training of finger, but without training, we can start the with the essence of the music. That is one dream which we are now working.
Okay, thank you very much. Okay, we have another 2 or 3 questions before we end. This question is from Rehan Abdul Kadir. In bio-inspired robotics, such as the elephant trunk, which structure on the elephant trunk do you focus on your study? Is it the muscle structure or the muscle attachment to the bone or the bone structure?
Elephant muscle has no bone. It's made of just muscle.
Mm-hmm.
And okay. Can you see here?
Yes,
Can you see?
yes, you can see.
Okay. And maybe question is talking about this one.
Yeah.
And the point is to realize, to generate a big moment in this kind of cantilever. You cantilever. There is two. There must be the two parts in the one section, cross section, which is tensile part and compressive part. Existing both parts realize the moment. Maybe if you have learned the strength of material, it's a very basic idea. So compressive parts and tensile parts, both parts are existing in the one sectional area. Is a key point to realize the bigger moment. And in this arm, we use two kinds of muscle. One is a contracting muscle, and the other is a extending muscle. By combining the two type of muscle, realize a big moment. And talking about elephant trunk, muscle itself generate only contracting force. It doesn't muscle in nature doesn't realize extending force. But so elephant trunks has two types of arrangement. One is in the axial direction, which generates the contracting force, and the other muscles are as located in the on the section line, which when they contract, the diameter of the diameter shrink, so they extend in the axial direction, which result in the which support the which result in the extended motion of the in the axial direction. So what I found in the elephant trunk structure, it consists of two parts on the section, which are compressive parts and extending part. That is that is what I learned from the elephant trunk.
Okay, I think we have the final question. The other question I will email to Professor Suzumori later because the time is very limited. So the final question is by Rino Ferdian. Thank you, Sensei, for the presentation. Soft robotics might also be driven by low energy source. Do the research also includes the development in low energy source? What will be the energy source that will be developed in the future, especially in driving soft robotics? So maybe, yeah, related to the source of energy. If you have any, uh, yeah, if, for example, the alternative solution rather than using air compressor, for example.
That's a very important point. And in some application, robot with taser is not a critical problem. For example, a colonoscope, which requires a software structure, but it can be taser, no problem. And of course, but taserless soft robot will greatly expand the application of important. So that is a very important one. One is supplying the energy from the outside. For example, laser or something. And I'm not sure, but all the researchers in software robots passing the taserless software robots are now thinking and has no solution now. But in my opinion, one potential idea is a chemical source. Chemical energy has a generally high energy density and very simple structure. It requires no complicated structure, but just material has energy. So I think one big potential is in the chemical material. But actually, all, all researchers are now working on and still get no solution.
Okay, thank you very much, Professor Suzumori, for your sharing as well as answering some of the question. So I'm very sorry for the other participant, Vincent Hong, Mufta, and the others. We will try to email Professor Suzumori, and we will try to get back to you later.
Yes, of course.
Okay, so because we are out of time, so again, I would like to thank you all, the participant today. So a little bit on the statistics, we have around 170 participants. So this is a very huge participants from WebEx as well as from Facebook Live. So they are joining from Facebook. So I would like to thank you everybody for your participation. And again, Professor Zumori, for your time as well as the sharing of the importance of soft robotics. For example, you have shared related on how soft robotics can be used for COVID, treating patient, developing healthcare product. I think it will be a new norm in the future, and maybe some of the students here, as well as some of the researchers, can explore some of the area like what Professor Suzumori was mentioning. I would like to close this session with one uh, um, saying by James Lovell, where he said that there are people who make things happen, and there are people who watch things happen, and there are people who wonder what happened. And I think to be successful, you need to be a person who makes things happen, I think. And we have seen many things happening in Suzumori Endo Lab that we can learn together. And I would like to thank again Professor Suzumori for your time. And just to share that Professor Suzumori is my sensei from Okayama University. So I have learned a lot from him. Thank you very much for the session, and hope we can meet again in other session. So thank you everybody for the time, and hope we can join in other future session that will be organized by the Office of TNCPI in collaboration with UTMShine as well as Cairo. So thank you very much. Assalamualaikum warahmatullahi wabarakatuh. Gotecho arigatou gozaimashita.
Thank you very much for your nice arrangement. I enjoyed.
Okay, thank you very much. Okay, Sensei. So we have recorded the session, and we will share the session later on. And I will take the question from the web, and I will email you later, and I will